Hello everyone, I am Gagan Laddha and the topic which we are going to deal today is a very important and basic topic of mechanical and civil engineer, that is shear force and bending moment. Now we all know about beam. What is a beam? Beams are the structural members which are used to support transverse load. Transverse load means the load which is acting perpendicular to the axis. Suppose this is a beam, the load acting perpendicular to the beam, the beams supports those transverse load. Now the question arises, what actually is shear force and bending moment? So to understand this clearly, suppose we have any cantilever beam and a load is applied in this beam. Suppose P load is applied at the end of this beam. Now what is actually is the effect of this load on this beam? To understand the effect, let us suppose we cut the section here, and to get the effect at this section, let us apply equal and opposite force P in this section. Okay. Now what will happen? This P and this P, this together will create a couple, and apart from this couple we have a force acting downward across the cross section. Okay. So if we try to draw the free body diagram of this, the free body diagram which we are going to get here will be a couple. The magnitude of couple, suppose the distance is x, the magnitude of couple will be equal to P into x. Okay. And apart from this couple, apart from this moment, a force will also act, and this force is actually acting on the cross section of the beam. So this force is nothing but the shear force. This force is acting on the cross section. Suppose the cross section of the beam is a square, the force P is acting across the cross section, okay, on the surface of cross section. So the force which is acting on the surface is actually shear force, and the couple this couple is trying to bend this beam. How can we say that this couple is bending this beam? Because this couple is acting on the same plane as that of beam. So whenever the couple acts on the same plane as that of the beam, it creates a bending couple, and when the couple acting perpendicular to the plane of the beam or plane of the shaft, whatever, then it creates a twisting couple. So this is basic difference between the bending couple and twisting couple. So what actually is happening when a transverse load is applied on a beam, it creates a bending couple. Apart from this, it creates a shear force. Okay, and in further unit we will see the effect of this bending couple and shear force. Because of this bending couple, because of this bending moment, bending stress X, whose magnitude is equal to m by I into Y, and because of this shear force, shear stress X, whose magnitude is equal to P A Y bar upon I into B. This we are going to see in the further units. Okay, so first step, what should be the first step? To determine the shear force and bending moment in any beam. Okay, so this is actually the shear force, and how can we determine the shear force and bending moment? See, how much force we are applying P force, and at the same time how much shear force is acting here? P. Okay, suppose I apply another force P here at a distance, suppose Y, then what will happen? Another counter force P has to be applied here, equal and opposite force. So how much shear force is now acting? 2P. And how much bending moment is now acting? That will be P into X plus P into Y. Getting this or not? So what I mean to say is, shear force is actually the algebraic sum of all the unbalanced forces either on the left or right side of the section. If we want to determine shear force at any section, just take left or right side of the section, take the algebraic sum of all the unbalanced vertical forces, that will be shear force. Okay, and what is bending moment at any section? Bending moment is nothing but the algebraic sum of all the moments on left or right side of the section. And when I am saying algebraic sum, obviously I mean there has to be some sign convention, some side has to be taken positive and another side has to be taken negative. Okay, so what sign convention which we are using is for shear force? The sign convention which we are using is run. Easy to remember. Run means right side upward is taken as negative, and accordingly we can create other things. Right side downward will be taken as positive, left side upward will be taken as positive, and left side downward will be taken as negative. So this is the sign convention for shear force. Okay, now what is sign convention of bending moment? We take sign convention as Suppose the beam is having a sagging moment. Sagging moment means the beam tends to smile, and when this beam is sagging, then the moment taken is positive moment. Okay, and suppose the beam is having the hogging moment. Hogging moment means the beam is trying to cry. How can a beam cry? Suppose we have a cantilever beam and a load is applied. Okay, what will be the elastic curve for this? Like this. So the beam is crying. How can the beam smile? Suppose we have a simply supported beam and a load is applied. Okay, what will be the elastic curve? Like this. That means the beam is smiling. So when we have a sagging moment, that sagging moment is taken as positive, and when we have a hogging moment, that is taken as negative. So this is the sign convention for shear force and bending moment. Now come to shear force diagram and bending moment diagram. Now what actually is shear force diagram and bending moment diagram, and what is the significance of the shear force and bending moment diagram? That is very important. Okay, so the shear force diagram is nothing but the graphical representation of all the shear forces across the length of the beam. Okay, suppose we have some loading, some complicated loading like this, any loading x, y, z. Okay, so at every point the shear force will be different. At every point the bending moment will be different. Okay, so what actually the shear force diagram is? Shear force diagram is nothing but the graphical representation of all the shear forces acting across the length of the beam. Bending moment diagram is the graphical representation of all the bending moment acting across the length of the beam. Now very important thing, what is the significance of the shear force and bending moment? Why the shear force and bending moment is essential? This is very important and very crucial. So I will take you to design part. If we want to design any beam, suppose we have any simple beam, suppose a beam which is acted upon by a UDL, suppose W per meter length. Okay, I am giving this example so that you can connect it and you can understand easily the significance of the shear force and bending moment diagram. Okay, so like this, suppose we are having a load on the beam and we have to design this. Okay, so whenever the designing is done, it always maximum stress is taken into consideration according to the strength criteria. Okay, so first thing we will have to determine the maximum stress. And for maximum stress, as we know the formula, m sigma is equal to m by I into y. For stress to be maximum, the bending moment has to be maximum. Okay, so for that we will have to determine the section where the bending moment is maximum. Okay, so suppose we are getting the shear force diagram in this like this, and the bending moment diagram is like this, suppose, for example. Okay, so the bending moment is maximum where? At this section, at suppose center. Okay, so one thing we can conclude it from here, that that maximum bending moment is occurring at center. That means maximum bending stress will occur at center, and we will have to design according to this maximum bending stress. Getting this? So how can we determine? So obviously this is a simple loading, we can have any complicated loading. So for that we will have to determine the maximum bending moment at the point where the maximum bending moment is acting. So for this, shear force and bending moment diagram is very useful because it gives shear force and bending moment at each and every point across the length of the beam. Okay, so this is the significance of the shear force diagram and bending moment diagram. Okay, so there are some certain basic rules in order to draw this shear force and bending moment diagram. The very first thing, kind of load, shear force diagram and bending moment diagram. Okay, so suppose there is no variation in load. Suppose we have a cantilever subjected to point load at end. That means no variation in load is there. And when no variation in load is there, the shear force diagram, obviously the shear force at every point will be same. The shear force diagram will be a rectangle, or you can say the uniform shear force diagram. Okay. Bending moment diagram, the curve of bending moment diagram is always 1 degree higher than that of shear force diagram. Okay. This we are having a horizontal line, that means x to the power 0 curve. So the bending moment diagram will be having x to the power 1 curve. That means a linear line. Okay. So shear force diagram is 1 degree higher than that of loading diagram, and bending moment diagram is 1 degree higher than that of shear force diagram. Just remember this thing. Okay, so another, suppose if we have a UDL, okay, suppose a cantilever subjected to UDL. UDL means horizontal load. That means already the curve is of x to the power 0 curve. Okay, so shear force diagram will be a x to the power 1 curve. Okay, so shear force diagram will be linear. Getting this? And obviously bending moment diagram will be of x square parabola like this. I'm just giving example to tell you that shear force is always 1 degree higher than that of loading, and bending moment is always, the curve of bending moment is always 1 degree higher than that of shear force. Suppose we have UVL loading like this. That means the loading itself is of x to the power 1 curve. The shear force diagram will be of x square parabola, and bending moment diagram will be of x cube parabola, and so on likewise. Okay, so this is the way how we can determine the curvature of the shear force and bending moment. Next is the relation between load, shear force and bending moment. That is W, F and M. Relation between load, shear force and bending moment. So as we have seen that shear force diagram, the curvature of shear force diagram is 1 degree higher than that of loading diagram, and the bending moment diagram is 1 degree higher than that of shear force diagram. This means when we differentiate bending moment with respect to x, we will get what? Shear force. And when we differentiate shear force with respect to x, we will get what? Loading. Okay, now this consists an important conclusion in itself. dm by dx is equal to f, shear force, or we can say dm is equal to f into dx. Okay, what is the meaning of this f into dx? Suppose for any loading diagram, what is the meaning of f into dx? Suppose this is a shear force diagram. F into dx means f is shear force into dx. Dx means a small distance. So what is the meaning of f into dx? This small area. Getting this? Okay. So if I want to get complete change in moment from suppose 1 to 2, just integrate this. And what will be integration of this f dx from suppose 1 to 2? There are 2 points. Suppose this point is 1 and this point is suppose 2. Okay, so integration of f into dx is nothing but the area of this shear force diagram between 1 and 2. So a very important conclusion we are getting from here, that m2 minus m1, change in moment between 2 points, is nothing but area under shear force diagram between those 2 points. Very important thing. Getting this? First thing. Second thing, df by dx is equal to w, or we can say similarly df is equal to w into dx. Okay, or f2 minus f1 is equal to integration from 1 to 2 w into dx. That means change in shear force between 2 points is equal to area under loading diagram between those 2 points. Clear or not? Okay, so these are the relation. Okay, second thing, this is first important point, that change in moment between 2 points is equal to area under shear force diagram between those 2 points. Second very important point, in order to have maximum bending moment, where the maximum bending moment, okay, so for that point what we have to do to maximize anything, we have to differentiate this with respect to x and equate it to 0. In order to get maximum bending moment, dm by dx should be equal to 0, or we can say dm by dx is nothing but f, or f is equal to 0. Another important conclusion, at the point where bending moment is maximum, for bending moment to be maximum, shear force should be equal to 0. Another important conclusion. Clear or not? Okay, so these are 3 to 4 things which are essential in order to draw the shear force and bending moment diagram. Now let us start drawing the shear force and bending moment diagram for different kinds of loading in different beams. Let us first take example of a simply supported beam which is subjected to a point load P at the midspan. We have a simply supported beam of length L and the point load P is acting at a distance L by 2 from each support. Okay. So the very first step in order to draw the shear force and bending moment diagram, the very first step is to determine the reaction. Okay, and the conventional way to determine the reaction is Ra plus Rb is equal to P. Now just take moment about any point. Rb into L is equal to P into L by 2. Therefore Rb is equal to P by 2 and so will be Ra. Ra and Rb are equal and that is equal to P by 2. Now there is a shortcut also for this. When you have a symmetrical loading, symmetrical loading means here the load is acting at equal distance from both ends, like this. Or suppose a simply supported beam which is subjected to a UDL. This is also symmetrical loading. Okay, so whenever you have the symmetrical loading, the reactions will be equal. Both the reactions will be equal and that will be equal to half of the total load. Getting this? Here both the reactions will be what? Total load is P. So both the reactions will be equal. Ra will be equal to Rb and that will be equal to P by 2. For example, here suppose this UDL is of W per meter length. Okay, so the total load will be equal to W into L. Sorry, small w into L. This is total load. So reactions would be equal to Ra and Rb will be equal to what? Ra is equal to Rb and that will be equal to WL by 2. So whenever there is symmetrical load, the reactions will be equal and that is equal to half of the total reactions. First thing. Now, once we get the value of Ra and Rb, now start plotting the shear force diagram and bending moment diagram. Okay. Now, in order to get the shear force diagram, first I will tell you the conventional way to draw the shear force and bending moment diagram. So for that, we have to consider these points A, B and C and we have to determine the shear force on just left and just right of each point. For example, point A we are having, we have to determine shear force at just left of the point A, just left of the point A and just right of the point A. Fa minus means this point, just left of point A and Fa plus means this point. Okay, and how have we defined shear force? Shear force is at any section is nothing but the total algebraic sum of all the vertical forces either on left or right side of the section. That means suppose we want to determine Fa minus. Okay, so total algebraic sum of all the forces, all the vertical forces is how much here? 0. No vertical forces acting here. Getting this? Similarly, what will be Fa plus? So when we get into this this portion Fa plus, now we have to see the total unbalanced force either on left or right side of the section. Okay, so how much is the unbalanced force on the left side of the section? We can see Ra. Okay, so this will be Ra. Now the question arises, or you can say this as P by 2. Now the question arises whether it should be plus P by 2 or minus P by 2. So just remember our convention. Left side, what was our convention? Right side upward was negative, left side upward was positive. So because we are saying the whole left of the section, okay, and this reaction is going upwards, left side upward is taken as positive. So this Fa plus is nothing but plus P by 2. Getting this? Similarly, Fc minus and Fc plus. Fc minus and Fc plus. What will be Fc minus? Just see all whole left side algebraic sum of all the vertical forces. There is nothing but Ra, which is equal to P by 2, since no variation in load. Similarly, what will be Fc plus? Whole left or whole right. Okay, when we see whole left, what we will get? P by 2 minus P. Left side upward is positive, left side downward is negative, P by 2 minus P, which is equal to minus P by 2. Or you can also see whole right side of the section, you will get the same answer. If you see whole right side of the section, it will be Rb, and Rb is nothing but P by 2, and sign will be taken as right side upward is negative, so minus P by 2. Clear? Similarly, FB minus and FB plus. What would be FB minus and FB plus? FB minus is again same as FC plus, since no variation in load. So this will also be minus P by 2, and FB plus is again 0. Clear or not? Now let us plot this shear force diagram. Okay. And this FA minus and FA plus shows the variation at that point. Okay, that means at point A the shear force varies from where to where, from 0 to plus P by 2. Okay, so just draw this. At point A initially shear force is 0 to plus P by 2. Clear or not? Okay, next FC minus and FC plus. FC minus is plus P by 2, FC plus is minus P by 2. Okay, and how can we join this line? The load is, since no variation in load is there, that means it will be a horizontal line, x to the power 0 curve. Okay, similarly FB minus and FB plus, FB minus is minus P by 2 and FB plus is again 0, again a horizontal line. This is P by 2. Clear now? So this is our shear force diagram. Now comes the bending moment diagram. Now how can we draw the bending moment diagram of this? So few things we will have to remember what I told you. The very first thing, for any simply supported beam, the moment at supports are 0 until and unless a concentrated moment is acting on this. So concentrated moment is not acting, that means moment at supports are 0. That means moment at point A as well as point B will be 0. First thing. Second thing, maximum moment will occur at a point where shear force will be 0. Okay, the shear force is 0 at this point, at the center point in this case. That means maximum moment will occur at center. And whether it be positive moment or negative moment, so just see the elastic curve of bending. This is a sagging moment. Because this is a sagging moment, so we will be having a positive bending moment at this point. Clear? Okay. Now the question arises, how can we join this curve? So here it is the curve of x to the power 0. So it will be x to the power 1 curve, or you can say the linear line. So we have to join this with the help of a linear line like this. Okay, and last thing, the magnitude which we have to determine. So I will tell you the easy way to determine this magnitude, and it will be helpful for most of the complicated questions. So how can we determine this bending moment? I told you one thing, that the change in moment between 2 points is nothing but the area under shear force diagram between those 2 points. Okay, that means change in bending moment between 2 points, MC minus MA. See how beautifully can we use this theorem. Change in bending moment between 2 points is nothing but area under shear force diagram between those 2 points. So what is the area under shear force diagram between those 2 points? P by 2 into L by 2, area of this rectangle. Okay, so this will be equal to PL by 4. Yes or no? Okay. And we know one thing, that moment at point A is 0. That means MA is equal to 0. That means whatever we are getting the change, that is nothing but moment at point C. That is the thing. Okay, in this theorem, obviously we can apply at those 2 points where at least moment at one point is known. Here we know that moment at point A is 0, so we can apply directly this formula and we can get the value of MC. So the moment at point C is nothing but PL by 4. Obviously the conventional way, we all know to determine the moment. How can we determine the moment at this point? MC is equal to RA into distance L by 2, which is equal to P by 2 into L by 2, which is equal to PL by 4. This is the conventional way. But this way will make the most of the complicated questions as simple. Getting this? So this is the way to draw the shear force and bending moment diagram. This was one of the example. Another example we will take. We have a simply supported beam which is subjected to point load, but not at center, at some eccentricity from center. Okay, that means the distance, this is suppose A, and this distance is suppose B, total length of the beam is suppose L. Okay, so how can we draw the shear force and bending moment diagram for this? So first thing is to determine the reaction RA and RB. Okay, so how can we determine the reaction? We know the conventional way, RA plus RB is equal to W, then take moment about point A, RB into L, RA plus RB is W, moment about A, RB into L, minus W into A is equal to 0. So RB is equal to W into A by L and RA is equal to W into B by L. Okay, so there is a shortcut also. You can directly write it. Okay, how? If you want to suppose there is an eccentric point load, then if you want to determine RA, this will be W into B by L. This distance for RA. RA is equal to W into B by L. RB is equal to W into A by L. So this RA WB by L, RB WA by L. First thing. Okay, now we have to draw the shear force diagram. Okay, now I will tell you the shortcut for the shear force diagram, and this shortcut obviously is valid for only point loading, for point load only, and not for other types of load. Okay, so how can you draw the shear force diagram? So remember one thing, all the point load of the loading diagram becomes a vertical line in the shear force whose ordinate is equal to that of the load. Getting this? All point load of the loading diagram becomes vertical ordinate of the shear force diagram, vertical line of the shear force diagram whose ordinate is equal to that of the load. Okay, what does this mean? RA is acting upward, left side upward is positive, the magnitude is WB by L, so this becomes a vertical line in the shear force diagram and whose magnitude will be equal to W into B by L. Getting this? Now from point A to C there is no variation in load, so it will be constant. At point C W load is acting, so we will have a vertical line whose ordinate will be equal to W. Okay, so a vertical line obviously downward whose ordinate will be equal to W. Ordinate means this distance is equal to W. What does this mean? If this is WB by L, then here it should be W into A by L. Getting this or not? Okay, and then again no variation in load, and then last is, that's it. Clear or not? So this is a shortcut obviously valid for point load only. You can directly plot the shear force diagram in case of point load, only if only point load is acting. Next, the bending moment diagram, we all know, ends 0, maximum at a point where shear force is 0. Line joint will be a linear positive side because of sagging moment, and magnitude MC minus MA, this will be equal to any area, either you can take whole left or whole right. So this much area under shear force diagram. How much is this area? WB by L into A, or you can say W into AB by L. So this will be WAB by L. That's it. Now there is a question which was asked in IES 2009. An overhanging beam ABC is supported at point A and B as shown in figure. This is point A, B and C. Find the maximum bending moment and the point where it occurs. So we have to determine the maximum bending moment and the point where this maximum bending moment is occurring. So in order to determine the position of maximum bending moment, first we will have to draw the shear force diagram. Okay, because the point where shear force diagram is 0, that point we will have the maximum bending moment. So in order to draw the shear force diagram, first of all let us determine the reactions. How can we determine the reaction? First, RA plus RB, summation of Fy is equal to 0. So RA plus RB will be equal to 8 kilonewton. First thing. Now take moment about A as 0. What we will get? RB into this distance, that is 2, is equal to 6 into 3 plus 2 into 1, or we can say RB into 2 is equal to, this is 20, or RB equal to 10 kilonewton. Okay. Now put the value of RB in equation 1, RA will be equal to minus 2 kilonewton. So these are the reactions which we are getting. RA is equal to minus 2 kilonewton and RB is equal to 10 kilonewton. Okay. Now how can we draw the shear force diagram for this? At point A, the reaction is minus 2 kilonewton. So just come minus 2 kilonewton downwards. Getting this? Now from A to C, no change in load, no variation in load, constant. At point A, 2 kilonewton downward, just drop 2 kilonewton again downward. So total it becomes now 4 kilonewton. Clear? From C to B, again no variation in load. At point B, total reaction upward is 10 kilonewton. Okay, and we have seen the total point load or total reaction at any point in the loading diagram will give a vertical line in the shear force diagram whose ordinate is equal to that of the reaction, magnitude of the reaction. Okay, so here we will have a vertical line and the magnitude of this vertical line will be equal to 10 and this is already 4, so this will be 6 kilonewton upside, positive. Again no variation in load and then the 0. So this is our shear force diagram. And from the shear force diagram it is clear that the maximum moment will occur at point B because at this point the shear force is 0. Okay, and in order to get the maximum bending moment, what can we do? This is point C and this is suppose point D. What can we do? MD minus MB, change in moment between 2 points, is equal to the area under shear force diagram between those 2 points. And what is the area of this shear force diagram? This is nothing but 6 into 1, that is 6 kilonewton meter. Okay, and we already know that moment at point B will be, moment at point D will be 0. So this is 0. Therefore, MB will be equal to minus 6 kilonewton meter. Answer. Okay, so maximum moment is occurring at point B and the magnitude of that maximum moment is 6 kilonewton meter. So according to the question, the answer is A, 6 kilonewton meter at the right support. That's it.